Hi, I'm Greg Kemnitz, and I'm co-founder and the CTO at Wirekite.io. Today, I'll be talking about efficient data handling in cloud databases, or why SQL Merge is your new best friend. In this talk, I'll be discussing cloud storage versus disk storage. Cloud storage is storage like Amazon S3, Google GCS storage, Oracle Cloud Storage, etc. These object storage models are all similar at a high level. Disk storage is traditional spinning disk storage, which is also available in the cloud if you use standard compute instances. Note that what I'm calling cloud storage databases use cloud storage as I described above. Many cloud-hosted databases use traditional disk storage. Examples of cloud storage databases include Snowflake, Databricks, and Firebolt. What I'm calling disk storage uses the good old-fashioned file as its storage primitive. You access and manipulate file contents using the traditional POSTGRES APIs of open, close, read, write, seek. File contents are mutable, and database engine developers have vast experience in handling and optimizing access to files. File storage is typically assumed to be local or in very fast storage such as storage area network appliances. Cloud file worlds provide SAN-like access to compute instances. Most database storage engines store row data as contiguous byte sequences in files. Indexes are also stored in a similar fashion as special types of rows, organized in storage in such a way to efficiently implement the index's layout strategy. Transactional data is also stored in files, as is metadata for tables, etc. Disk-based storage engines typically use fixed-sized pages as their primary row bucket. The idea behind pages is that pages are easier for file systems to read and write in a single operation. It's also worth mentioning that database engine buffer pools manage pages in these environments. Cloud storage is fundamentally about managing objects. Objects are bunches of bytes, similar to files, but objects are immutable. Once an object is created, it can't change. It can only be read or removed. This means objects can't be edited. If you want to change the contents of an object, you have to read it in, make your change, write your bytes out to a new object, and remove the old object. This can be simplified by overwriting the old object while keeping the same name, but it's still a logical object replacement. Object edits are expensive. Storage engines and cloud databases use objects as their equivalent of disk pages. Multiple rows will be stored as in individual objects, and most objects store rows belonging to individual tables. There is typically metadata also stored in objects that maps sets of objects to specific tables. Indexes, table high-level metadata, transactions, and all such other database things are implemented similarly. Cloud database engine buffer managers all manage objects. What's so good about cloud storage? It has the usual cloud goodness. The cloud provider manages crash recovery, data centers and operation issues, and spends vast sums and devotes extensive talent to getting this right. In terms of application goodness, access via cloud APIs can be heavily parallelized across both individual threads and across numerous application instances. The immutability of objects enables a vast degree of parallelism that isn't easily available in traditional file storage. Bulk read operations are therefore a whole lot faster, as access can be massively parallelized. Cloud storage is Great for read-heavy, parallelizable write and bulk workloads such as data warehouses and OLAP. Cloud storage characteristics. Cloud storage is fundamentally about managing objects. Objects are bunches of bytes, but objects are immutable. Once an object is created, it cannot change. It can only be read or removed. This means that objects can't be edited. If you want to change the contents of an object, you have to read it in, make your change, write your bytes to a new object, and remove the old object. This can be simplified by overwriting the old object while keeping the same name, but it's still a logical object replacement. Object edits are expensive. Storage engines in cloud databases use objects as their equivalent of disk pages. Multiple rows will be stored in individual objects, and most objects store rows belonging to individual tables. There's typically metadata, also stored in objects, that maps sets of objects to specific tables. Indexes, table high-level metadata, transactions, and such things are implemented similarly. Cloud database engine buffer pools manage objects. So, what's so good about cloud storage? It has the usual cloud goodness. The cloud provider handles crash recovery, data center and operations issues, etc., and spends vast sums and devotes extensive talent to getting this right. In terms of application goodness, access via cloud APIs can be heavily parallelized across both individual threads and across numerous application instances. The immutability of objects enables a vast degree of parallelism that isn't easily available in traditional file storage. Bulk read operations are therefore a whole lot faster as access can be massively parallelized. Cloud storage is great for read-heavy, parallelizable write and bulk workloads such as data warehouses and OLAP. What's not good about cloud storage? Operations that can't be easily parallelized can be very slow when compared with disk storage. In particular, classic database transactions, which have to be single-threaded and sequentially executed, may end up forcing large numbers of object replacements as individual row contents are updated. Cloud storage is not great for OLTP workloads where transactions are small and individual records are frequently changed. What if you need to do a bunch of row-level changes? Most OLTP worlds use a database engine that uses file storage and pages for their production data store. They often propagate changes to cloud databases and use these data worlds as data warehouses, vector stores, etc. In order to make this work efficiently for large-scale changes, you have to figure out how to turn your row-level changes into bulk operations, so the cloud database can execute your changes fast enough to keep up with your OLTP workload. In order to do this, you have to identify a unit of work that's bigger than small transactions and ideally big enough to be sensibly bulk. Assemble the changes that fit into your unit of work into a list of changes, push your changes to the target cloud database, and execute your changes. All this is nice, but how do we do this in real life? Cloud databases really want to be bulk managed. Large-scale data injection operations are straightforward, but updates and deletes are painful. In particular, single row update sucks. You can sort of work past this with upsert and big deletes with long in lists, but both of these have query generation complexity and query text length issues in some databases. You want a way to simplify these and run them as bulk operations. SQL Merge to the rescue. Merge is a relatively new addition to SQL, intended to handle just the sort of bulk change operations that we've been discussing. Merge takes a target table, a shadow table, join logic for these, and edit directives for insert, update, and delete. Merge can be structured to use the contents of the shadow table and execute inserts, updates, and deletes on the target table in a single bulk operation. Once merge completes, all changes have been applied to the target table. Merge will either completely succeed or completely fail, simplifying crash recovery considerations in your application logic. Care and feeding of SQL Merge. The high-level idea behind our use of merge is for every table you merge, you have a shadow table that has the target table schema plus some metadata columns to execute the merge. This metadata includes an indicator of what to do in the merge, I for insert, U for update, D for delete, a copy of the primary key for joining, and all the columns of the table. For each column, there's also a marker column, only used for update, that indicates whether to update the target table column using the shadow table's column value or to use the existing value that's already in the column table. Therefore, the shadow table will have 2 times number of columns in the target table plus the number of primary key columns in the target table plus an additional column for the indicator. In order to load the shadow table, we need to create a CSV type file with the shadow table's intended contents. We'll then load the shadow table using the database's fast CSV ingestion command, and then we will construct and execute the merge SQL, truncate the shadow table, and we're done. Implementing merge. Consider a table. Foo, A as an int, B as an int, primary key of A. Foo has 3 existing rows with the values 1, 1, 2, 2, and 3, 3. We want to do the following operations. Insert a row 4, 4, update 1, 1 to 1, 9, and the row with 2, 2 to 2 null, and delete the row 3, 3. To execute our merge, we need to populate our shadow table. The shadow table will have the following schema. Foo merge, op as a char, A underscore PK as an int, A underscore flag as a char, A as an int, B flag as a char, and B as an int. The flags can be chars, ints, or booleans, anything that can efficiently hold a single do something value. In our case, the do something value will be y. We build a CSV style load file. The below comments won't be in the load file. \n means null. The first column of the CSV file is the column indicator. The second column is the joining key, which is the primary key in the target table. The columns after the second are the flag value pairs. A flag value of y means the value in the shadow table, and the CSV will be used for update. Any other value, n or null, means that the value already in the target table will be used in the update. Effectively no opping an update on this column. This approach allows this scheme to support sparse updates that update some but not all the column values. Note that insert and delete do not use the flag columns. We will load this file to the foo merge table using the ingest CSV command, whatever it is. It is usually something like copy, and in many cloud databases, this copy operates on a storage bucket, so our app will have to transfer the CSV file to the storage bucket before running the ingestion. Now that the data is in our foo merge table, we now build our merge SQL. IFF, condition, true value, false value, is a simplified version of case supported by some DB engines, particularly Firebolt, and we're using it here so the query text can fit on the slide easily. Below is the Firebolt syntax for merge. Merge may have slightly different syntax on different databases, but it has the same high-level logic and behavior. Matched is syntactic sugar for the on condition being satisfied, which is the primary key equality in most cases and in our example. Merge into foo as f, using foo merge as m on f.a equals m.a. When matched and op is u, then execute this update. When matched and op is d, do a delete. When not matched and op is I, then do this insert. Note the updates. The IFF logic is where we determine whether we're using the value from the foo merge table or the value that already exists in the foo table. In order to use merge in this way, we want all columns in foo have to be specified in the update subcommand. We will now do the following to execute the merge. Run the merge SQL itself using the appropriate client API call. Run truncate table on the foo merge table so it can be used in another merge. Clean up the application world. Remove the CSV file, possibly remove it from a storage bucket if we used one, that sort of thing. Implementation considerations. Because of how when matched works, each record in the foo merge table must be unique based on its primary key. If your unit of work includes multiple operations on the same row, you will need to build a single operation to hand to the merge itself. For example, an insert on a new row followed by updates to that same row will have to build a real insert that includes the updated values, and the final insert is the one that will be used to load the merge table. Note that merge will lose individual transaction boundaries, so you should only use merge in situations where you never roll back. Why is merge faster than row-level SQL? Some viewers may call BS. Why is merge faster versus a sequence of insert, update, delete that do the same thing? Merge seems to be doing more work as we have two tables to muck with, a file to generate and load, and still have to run SQL with a join. Well, here's the magic. Merge row operations can be easily parallelized by a parallel-friendly DB engine, which most modern DB engines are, particularly cloud DB engines. Merge allows operations to be logically summarized by the buffer pool. This minimizes rewrites of objects, ideally to a minimum of a single object rewrite per merge entry that affects that object. Merge doesn't have row-specific literals in the query text. It's far less likely to hit query text limitations, which becomes an issue if you're handling large numbers of row operations. More on merge. A single merge can be used with thousands or millions of row-level operations on a specific table. Merge is the most viable way to turn single-row sequential operations into database-friendly bulk operations. It's worth mentioning that merge can be simulated with join insert, join delete, and join update, but if merge is available, it should be used, as it will be faster than these three queries as well as simplifying crash recovery. Merge is particularly helpful with cloud databases, but it can be used with any database engine that supports merge with significant speed up versus large sets of single row queries. A bit of hard data from Firebolt. A bunch of single row queries at most 30 ops per second. A 500,000 row merge completes in about 28 seconds, including the push to the bucket, load, merge, truncate, and cleanup for a throughput of 17,800 rows per second. The parallelization and I/O reduction features of merge are still relevant in DB engines using traditional disk storage, assuming your unit of work permits. Thank you. Thank you for watching this video, and I wish you success in handling your cloud data worlds using this approach. Here's my contact information. I'm Greg Kemnitz, and here's my email and stuff. And please consider using wirekite.io for your data movement and data migration needs. Thank you again, and goodbye.